You won't see it coming, guys. You won't. Okay guys, so let's try and answer the question of what is the sum of 1 minus 1 plus 1 minus 1 plus all the way up to infinity. We're gonna be just extending this alternating sum. We're gonna be just adding and subtracting a 1 well, forever. So what is this thing gonna be equal to? A 0, a 1, a negative 1? Well, let's check it. I would like to call this guy S. S is gonna just nicely stand for a sum. I would like you guys to consider what will 1 minus S be equal to. So 1 minus S is gonna be 1 minus 1 minus 1 plus 1 minus 1 plus all the way up to infinity. So by distributing this negative sign all over the place, what we will get is that this is actually equal to 1 minus 1 plus 1 minus 1 plus, well, all the way up to infinity. But wait, what is this thing? Well, this is the sum S we originally started with. And so, well, did we just get that 1 minus S is equal to S? Well, that will mean that double S is equal to a1, and so S is equal to 1 over 2. Is it possible for just a sum of, well, a bunch of integers to be equal to a half? Well, let's see. This proof isn't very rigorous, as you might have already noticed, because what I do here is I just distribute a negative 1 to infinitely many numbers, and we have honestly no idea whether the distributive law of, well, real numbers will work as we approach infinity. It's something we just don't know. We take it as an axiom, but who knows what happens at the infinity. So I'd like you now, guys, to see a more rigorous proof of mine of, a more rigorous way to prove that this sum is actually equal to a half, because it is beautiful, I think. So how can we rewrite the sum 1 minus 1 plus 1 minus 1 all the way up to infinity? Well, we can rewrite it as the sum, as n goes from 0 to infinity, of negative 1 to the power of n. Okay, well, this looks awfully a lot like a geometric series, and we actually know how to calculate, well, geometric and in particular infinite geometric series. We know that a series from n being equal to 0 up to infinity of x to the power of n will be equal to 1 over 1 minus x for all x's that are between negative 1 and 1. But, oh man, like, you see, this negative 1 here doesn't really satisfy the condition of x being between negative 1 and 1, because, well, negative 1 is equal to negative 1 is not strictly greater than negative 1. It's going to be pretty tough for us to plug negative 1 in here to this formula. Okay, but, well, we could at least try and calculate maybe a limit as x will approach this negative 1. Well, what is this stuff going to be equal to? So let's try and do it. I would like to calculate the limit as x approaches negative 1 of the sum as n goes from 0 to infinity of x to the power of n. Well, this thing's gonna be just the limit as x approach. Oh, I forgot to say it's gonna approach the negative 1 from above. So it's gonna be the limit as x approaches negative 1 from above of 1 over 1 minus x. Well, this is clearly gonna be equal to 1/2, but you see, the problem is that it's just a limit. We have no idea if the value of this of the series, a geometric series, is actually going to be equal to that 1/2, because, well, as you probably know from, I don't know, school, high school, calc, whatever, that the value of the function does not necessarily have to be equal to its limit at that point. So for example, this is going to be my point x0, and as you can see, the limit is, well, this particular value of y. However, the actual value of the function is this thing right there. It doesn't really have to be equal to the limit. Okay guys, so my camera died, but, well, that's just a formality as always. So once again, getting back to the problem statement, well, we have no idea whether the value of the limit of a function is actually going to be equal to the value of the function itself at that particular particular point, at a particular x value. And so, well, this limit, it doesn't really tell us anything about the result, the final result. So how are we supposed to solve it, for God's sake? Well, we see that, well, this condition of x being between -1 and 1 can be interpreted, well, kind of like the domain of this function right here being, well, between -1 and a 1. Okay, but, well, there is a nice thing, a nice, let's say, mathematical approach to domains, and this is so-called analytic continuation. So we can just kind of take this lovely domain and just expand it out further. Well, how are we supposed to do it? First of all, I would not want to expand the domain of this particular function. I would like to actually change this function a little bit. I would like to take myself a sum as n goes from 0 to infinity of -x to the power of n, because it's going to be just equal to 1 over 1 plus x, which is, 1 over 1 minus x. That's going to be 1 over 1 plus x. Awesome. And I would like to expand this guy's domain so that it will actually take in the x being equal to a 1. So how do I want to do it? There is this beautiful thing called the Taylor series. The Taylor series gives us an approximation for every single function, a differentiable function, centered around some particular value. So if I want to approximate this function, I would have to take myself a sum as n goes from 0 to infinity of its nth derivative at some kind of an a, which is the center, the point on which I would like to center that approximation, divided by n factorial, and then multiplied by x minus a, everything to the power of n, where once again a is the x argument I want to center that approximation around. Also, so, well, what are the derivatives of 1 over 1 minus x? Well, we see that the 0th derivative is going to be equal to the function itself. That's going to be 1 over 1 plus x. The first derivative is going to be equal to -1 over 1 plus, 1 plus x squared. Gotta be hairy. Gotta hurry, because my iPad's going to die here. So, that's going to be 1 plus 2 all over 1 plus x to the power of 3. And actually, we are kind of starting to see a pattern here, that the nth derivative, that was supposed to be an n derivative, would be equal to -1 to the power of n multiplied by n factorial, all nicely over 1 plus x all to the power of not 3, but n plus a 1. We probably will have to prove this one by induction for this proof to be 100% rigorous, but, well, I will leave it, let's say, as an exercise for you guys to do it, let's say, down there in the comments below. Okay, so, well, we have the nth derivative of the function. Let's just plug it in here into the Taylor series, and let's evaluate it at the a. I haven't really decided on what I would like a to be yet, but I will do it in just a matter of seconds. So that's gonna be the sum -1 to the power of n times n factorial all over 1 plus that a, because I'm evaluating, recall, this nth derivative at a, as here in the formula given, and then I will multiply it by x plus x minus a all to the power of n divided by, and then factorial. Those two factorials will cancel each other pretty nicely. That's pretty nice. And then what I will get is the sum as n goes from 0 to infinity of. Then I would like to suck this -1 here inside this x minus a to the power of n, because those are both raised to the power of n, so there's no problem for me to just go on and multiply those guys out. What I will get then is negative a, maybe not negative a, I will get x, a minus x, now it's finally is good, all over the a plus 1 all to the power of n plus 1. I can pretty lovely go on and rewrite it just to maybe, simplify it a little bit with all of those exponents. At least for me, it's gonna be a simplified version. A minus x all over a plus 1, everything to the power of n. And, well, doing the how to say it, man, the convergence test, we will get the A has to be, I mean, once again, we have to get some kind of an A that will be, well, close enough to a 1 here on the number line. So, well, we have quite a few options there. Let's maybe choose, I don't know, 3/4. Why not? It's just gonna be a nice value. I have no idea why I chose it, honestly. I just like it. So let's plug it into here. So what we're gonna get is the sum as n goes from 0 to infinity of 1 over 3/4 plus 1. And then 3/4 minus x all over 3/4 plus a 1 to the power of n. And we see by the convergence test, by the, how to say it, it was, I think, whatever, the ratio test, we'll get the x is gotta be between -1 and 5/2. I'm not gonna be doing this right now, honestly. I'm just too lazy for that, but you can definitely go on and do it by yourself as an exercise. It's just a little bit of arithmetic. Yeah, so that's gonna be x between -1 and 5/2. Well, that's awesome, because as you can see, our 1 is inside of this range, so well, that's lovely. But now a nice thing is that this is actually a lovely geometric series which will evaluate to a divided by by 1 minus r, where r is our common difference, which is gonna be this thing right there, and where a is the first how to say it, the first term of the sequence is going to be this 1 over 3/4 plus 1. And so after you evaluate all this stuff and do a bunch of arithmetics, you will actually get that this thing is pretty likely equal to 1 over 1 plus x. That's lovely, because, well, it actually turned out to be the same function. I mean, the same looking function as the guy right here. They have different domains, so they are not the same functions, but they are, well, similar looking, which, well, it didn't have to happen, but it did, so it's, you know, pretty lovely and awesome. So now what we can do is just, you know, plug in, because I can just say it's gonna be equal to this our new function, this sum from 0 to infinity of that -x to the power of n. Yeah, this is my new function, and now I can just, you know, without the problem, plug in a x equal to 1 here, because it's inside of the domain, inside of the range of convergence, and say that the sum as n goes from 0 to infinity of -1 to the power of n is equal to 1 over 1 plus 1, which is equal to 1 over 2, which is a half. Oh man. This proof is a little bit more rigorous, though. Well, I mean, always analytic continuation is just a weird kind of stuff. Like, now, when you analytically continuate the Riemann zeta function, you will get that the sum of all of the natural numbers is equal to -1 over 12, which clearly does not make sense. But who cares? I mean, it's, you know, math committing suicide here. So once again, what did we do here in this problem? Well, we first of all we write our sequence of those alternating negative and plus ones as the sum as n goes from 0 to infinity of -1 to the power of n. Then what we did is we tried to get it, we tried to get the point where we would be able to use this formula for the sum of a geometric progression, the infinite geometric progression, with the absolute value of x being less than 1, which is that the sum of all those x to the power of n is going to be 1 over 1 minus x. But, well, we couldn't really do it because, well, the absolute value of -1 is not really less than 1, which is pretty shitty. But what we did then is we just, well, kind of try to analytically continuate this lovely, where is it? The domain of that function using our, Taylor series right here. Then what we did is we got a lovely convergence sequence with a radius of convergence which covers our desired x being equal to 1. Then we just substituted our x being equal to 1 into the sequence we got, into the function we got out of that stuff. And we actually got that the sum of those alternating ones is equal to a half, which is, man, why the hell? Okay, so I really hope you guys enjoyed this video, and see you in the next one. Bye.